So we all know the definition of a linear function, and we will try to. Do you know something about the adjoints? I think we did something about regarding this. I mean, definition of an adjoint. I think the first portion of this section treats with linear functions on an inner product space. Okay. Are they defining T star here? Have we defined T star in the linear functional section? No, 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 no. I think we haven't. So our first theorem is that V be a finite dimensional inner product space. I think I refer to this result, I mean, a number of times, but we only proved it for c to the power n, and we couldn't prove it for, I mean, an arbitrary finite dimensional vector space, because I kept telling you that we need the notion of inner products to do it. This is one way Rees representation theorem. Let V be a finite dimensional inner product space, and if a linear functional on V, then there exists a unique vector in V such that if alpha is alpha inner product beta. Okay. So basically they are saying that this any linear functional is uniquely characterized by a vector in V. Okay. So how are they coming up with the vector? So this is, say, an orthonormal basis. They are putting this to be the vector. Beta equals to this. Okay. And let if beta be the linear functional defined by f beta alpha. Okay. Then you realize that f beta on alpha k, that is, they are evaluating f beta on that basis. You get f alpha k. So since f beta and f matches on the basis, they matches on the whole vector space. Now you might ask, why all of a sudden you come up with this vector? I mean, how do you get the intuition? So, I mean, I can tell you, like, in a way, maybe, I mean, what should I say? So, suppose if alpha is like, if alpha is, there is some beta. So, I mean, the intuition comes from dot product actually. If you look at it carefully, hmm, you will realize that the intuition actually comes from dot product. Like, uh, suppose if alpha is like, suppose beta is some ci alpha I. So you get alpha inner product ci alpha I. That is, you get ci bar alpha inner product alpha I. Okay. So you see the coefficients of beta are of this, I mean, are coming out, right? So in a way you are getting an intuition like how to do it. I mean, just I'm trying to give you an intuition. alpha, the 3 alpha inner product this beta y1 alpha 1 yn alpha n would be this. If f is any linear functional on V, then f has the form c1 x1 cn xn for some fixed scalars c1 to cn determined by the basis. Of course, cj f alpha j if we wish to find out. Yes, this is something I was talking about. This is the thing. You look at this. This is very good. Look at this thing. So suppose we want to find vector. Okay. So for any alpha you write this, and suppose beta is this. Okay. Now you are willing to find the yi's, right? The coefficients of beta. So what is alpha in our product beta? That is x1 y1 bar, right? Right. If f is any linear function on V, then f has the form f alpha on this. You remember, I hope, because I mean f is of the form, suppose f alpha. So what is that? I mean, like summation ci alpha, no, sorry, summation say if alpha 1, so summation alpha is like xi alpha I. So after multiplying you get summation xi if alpha I, right? So you can write if I to be if alpha I. So these are fixed constant because f is being evaluated on the basis. So you can write it like ci alpha I, ci xi, where ci is f alpha I, right? So now you look at here. So if f alpha is alpha inner product beta, for all alpha, you have to get C1 is equal to Y1 bar, right? Yes, that is. So Yj is F alpha J bar. That's it. Okay. So that's how you, sort of a back calculation. There is a comment like brief, but it fails to emphasize, like further, the proof of theorem 6 that have given is admirably brief, but it fails to emphasize the essential geometric fact that beta lies in the orthogonal complement of the null space of F. Orthogonal complement of the null space of F. Okay. And let W be the null space of F. Beta lies in the orthogonal complement of the null space of F. Okay. Beta lies in the orthogonal complement of the null space of F. So they are saying that beta belongs to NF part. So if beta is in NF, okay, I understand, then beta will kill every vector. That's true. And if any vector is in NF, and if alpha is in NF, then alpha inner product beta, that is basically f alpha, okay, it is 0. Right. So alpha is in the orthogonal complement of NF, right? In fact, if P is the orthogonal projection V on W perp, then if alpha is f of P alpha for all alpha. Hmm. This is very important. This is very important. Okay. So let's see example 16. তোমরা একটু দেখো example, have a look at this example, that why the result is no, I mean why the fact that the finite dimensionality of V is needed. Okay, so let's move on to the next result. For any linear operator T on a finite dimensional inner product space V, there exists an inner product, yeah, there exists a unique linear operator T star on V such that T alpha inner product beta is alpha T star beta. Okay. So we will define what T star is in a moment. So T alpha inner product beta is T star beta. Okay. So beta be any vector in V. Okay. So now send alpha to T alpha inner product beta. See, this is a linear operator. Okay. Okay. You understand that beta is a fixed vector. So along with beta, you are sort of assigning a linear functional which sends alpha to T alpha inner product beta. Okay. By theorem 6, there is a unique vector beta prime in V such that T alpha beta is this. Okay. For every alpha in V, let T star denote the mapping beta from B prime. Okay. Now they will show that this is indeed a linear map. I mean, T star sends beta to beta prime. So let's see whether it is a linear map or not. And after some elementary checking, you will see that T star indeed is a linear map. Okay. So for uniqueness of T star is clear, because I mean, you will one thing you will be able to see actually, because I mean we will use the same technique. Suppose if alpha V is equal to say what should I say, alpha W for all alpha, then we will immediately write alpha equals to V minus W is 0, choose alpha equals to V minus W and get this is 0 and V equals to W. So this is the technique we use to prove uniqueness. I mean whenever we are in an inner product space. Okay, so V be a finite dimensional inner product space and let beta be an orthonormal ordered basis, T be a linear operator on V, and let A be the matrix of T. Now see, T and T star, you saw how we got T star from T, okay? And T star was a linear map from beta to beta prime. Okay, there is actually a way where they define T star from V star to V star. Okay, just let me make a remark. You understand that T star is sending beta to beta prime, and you have already seen that for any linear functional f, you can sort of associate a beta. So you can think of T star as a map from V star to V star, which sends f to f compose T. Just keep it in mind. We will do things more in a more clearer way. In a clearer way, just I mean, okay. So the point is that they want to make is that if this is the ordered basis, if E is the matrix of T, then basically what they want to say is that this is the matrix of beta star. T be the linear operator on V and E be the matrix of T in the ordered basis beta. Sorry, no, there is no T star. They are only talking about T. So EKJ is, they are saying is that is like this. So alpha they have defined this way for any vector. Now T alpha j is EKJ alpha k. Yeah, of course. And this relation we have established it. Okay. In the first section of this chapter, we have established this relation. So T alpha j is this, and also T alpha j is of this form. I mean, from this here, and this is the general expression of evaluating a linear map on a basis. Hence, you get this equality. I mean, AKJ is this, right? Now, I think they will tell something. Yeah, that was something I was talking about. Just read corollary. This corollary, please go through it. You will realize that the matrix of T star is basically A star, the conjugate transpose of A. Just go through it. This corollary, please. হ্যালো, কি 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 হচ্ছে? হ্যালো, হ্যাঁ বল। হ্যাঁ বল। কাজে লাগবে না? ও আজকের জন্য, হ্যাঁ হ্যাঁ হ্যাঁ, সরি সরি সরি। আরে ওই দাদা তো বসবে বলেছিল, এবার সে দাদাকে ফোন করে দেখি বিয়ে বাড়ি থেকে আদৌ ফিরেছে কিনা। তোর কম্পিউটার হয়তো লাগবে না, ইনফ্যাক্ট তোর দাদার কম্পিউটারটা লাগবে, তোকে তুই শুধু বসে থাকলেই হবে। তবে অন রাখ, অন রাখ কম্পিউটারটা, মানে বলা যায় না। আচ্ছা ঠিক আছে, দাঁড়া দেখছি। ফোন করছি, দাঁড়া। ঠিক আছে ঠিক আছে, লিঙ্ক লাগছে তো, লিঙ্ক হয়নি। ও আচ্ছা, ঠিক আছে। মানে বাড়ির লোক এভাবে ভাবছে ফেব্রুয়ারি মাসে ডেট লাইন হয়, ডিসকাশন এন্ড। আচ্ছা দাঁড়া, আমি দাদাকে ফোন করে বললে করছি। Okay, so let's uh, yeah. So clearly you saw that the conjugate transpose of the matrix is the matrix of T star. V be a finite dimensional vector space in an inner product space. E orthonormal projection of V on a subspace W. Then for any vectors alpha and beta in V. So uniqueness topology E star for any vectors alpha beta. This okay. So you realize they are sort of proving that E star is E. Hmm. Yes, this T star is called the adjoint of T. Hmm. By theorem 7, every linear operator on a finite dimensional vector space, inner product space, has an adjoint called the adjoint of T. Yes, this is a very important thing. The adjoint of T, you realize it depends on the inner product given on the vector space as well. It's more complicated. Okay. Similarly, you can define like example 18, example 19, where they are basically see, the example 19 is sort of the inner product this a b and n v is like c to the power n cross and matrix over the entries. The adjoint of the linear operator ax is the operator a going to a star x. Okay, this is natural, na? I mean, the matrix of t is a, so then we show that the matrix of t star is a star. So for a matrix a, the adjoint should be a conjugate transpose of a, right? Mhm. So suppose V is like MNC, hmm, and the inner product is stress. Now, where is the yes the operation is, I mean the operator is left multiplication by a fixed matrix, say M. So you send any matrix to MX. They are trying to find out M star. Okay. So what is M, LM A inner product B? That is B star MA, right? Because LMA is MA, that is MA B star, and that is AB star M, that is trace this, and you get this. Okay, so clearly you realize LM star is basically nothing but LM star. Okay, LM whole star is nothing but LM star. So these sort of nice results, I mean, things that should happen will happen. No adjoint theorem. So, example here. Okay, have a look at example 20. Have a look at example 20. You have 3 4 minutes. So this is another inner product given over the field of complex number. If f is a polynomial, f bar is this. The multiplication by f. Okay. That is mfg is mg. They are claiming that this operator has an adjoint, namely if bar. So mfg inner product h is fg inner product is fg, so on and so forth, and you end up getting this. So it's not like no operator on a finite dimension, on an infinite dimensional vector space will on an infinite dimensional inner product space will ever have an adjoint. It may or may not have it. Hmm. Some may do and some do not. We will inner product space. The differentiation operator on Cx. The integration by parts shows that okay. So df inner product G is this. So they are saying that you do this inner product f prime G and all that. After doing all this, you end up getting this. Let us fix G and inquire whether there is a polynomial discharge G such that df inner product G is this. Okay. So there's supposed to be a contradiction. So if d star G exists, you will get this, and you will get if inner product d star G plus f dg is this. So you are sort of doing the inner product G prime plus G, that is if G prime bar plus G bar, you are doing this inner product. Okay. Now with a fixed G, you get this. If is this is a linear operator of the type example 16 cannot be of the form if inner product H. Okay. So you understand, what they are saying is a linear functional of the type considered in example 16. What was example 16 by the way? This. Hmm. So it can't have an inner product. I mean, have an operator. I mean, have an adjoint. If we choose any g for which this is not equals to 0, hmm, hmm. So existence of suitable register g implies g0 equals to g1 equals to 0. We do have uh, so what happens of the form this unless L equal to 0. Acha. If d star g exists with h equals to this, we have LF is this and so this. The existence of suitable polynomial d star g implies g0 equals to g1 equals to 0. Conversely, if g0, okay, any g for which g0 is not equal to 0 and g1 is 0, we cannot suitably define d star g. Achha. We conclude that he has not joined, right? Okay, I mean we will complete this section on the next class and we will move on to the exercise. Okay. Today's class was a bit short actually. I mean I'm messed up in so many things.